Good morning, ladies and gentlemen. And today I'm glad to give the topic about the study of CO2 chemical absorption and industrial application. So I'm from Zhejiang University. So the main contents including four. First is the background, then second study of CO2 chemical absorption, and then I will introduce 150 kiloton per year CO2 chemical absorption demonstration projects and the conclusion. And then first I will introduce the background. As you know, now China is the largest CO2 emission country, near 10 billion ton CO2 per year. It's account about 30% of the global CO2 emission. And this is because China is the largest coal producer and consumer. Near 4 billion ton per year coal is consumed, almost half of the world. So the coal-fired planet account about 70% CO2 emission in total CO2. So, you know, China now government already announcement that China will attain the CO2 emission peak in 2030 and will try to attain the carbon neutralization target till 2060. So CCUS is one of the important technologies to achieve carbon neutralization. There are a lot of CO2 capture technology, as you know, but post-combustion capture now is an effective way to achieve CO2 great reduction from fossil fuel. And this is a typical chemical absorption process. So the flue gas from the boiler first go to the pre-treatment part to cool down to about 40 centigrade C, and then sent to the absorber. In absorber, the aiming is inject into the absorber to absorb the CO2 from flue gas and become a rich solution, and then pass the heat exchange to heating, and then sent to the stripper. In the stripper, we use steam to heating the stripper to about 100 centigrade C, and then the solution emit the CO2, and then the become a learned solution, and the learned solution can recite back to the absorber to recycle to absorb the CO2 again. So it's the typical technology. And then the flue gas to the top, and to use water washing to absorb some of the amine and the degree amine emission. And finally, the CO2 released CO2 is cooled down and use a compressor to high CO2 pressure for utilization. So the advantage of this chemical absorption process is usually this process is suitable for complex flue gas condition, mature technology, and easily industrial application. So in this world, now more than 90% CCUS projects use chemical absorption technology. One of the largest one is Boundary Dam CO2 capture projects. It's 1 million ton per year, operated 2015. And second one is in the Petrolavo is CO2 capture projects. It's 1.4 million ton per year CO2 capture capacity, operated 2017, and but closed because of the economic problem, and now will restart again. And in China, there are two largest CO2 projects. One is in the Shanghai Shidongkou power plant. Is 120 kilotons per year CO2 capture demonstration project by Huarun Group, operated in 2008. And Second one in the belong to the national energy group. Taizhou power plant is about 0.5 million ton per year CO2 projects operate this year. And now there are a lot of research about the chemical absorption. Usually they focus on the two targets. One is how to decrease energy consumption. So for these targets, usually focus on the advanced solvents development and then process optimization. And the second one, how to decrease the capital cost. This process focuses on the new reaction with low price materials. And second one is mass and heat transfer intensification to decrease the size. And so first, I just believe first introduce the solvents development. So solvents development from the 1930, so usually we call the first generation solvents, typically like MEA and MDA. Usually MEA is for chemical absorption process. The energy consumption is high. I can attend 4 gigajoule per ton CO2, and it's also it's corrosive and degradable. And so then a lot of research focus on the developers called second generation. Typical one is mixed amine, like shell company developed called DC mixed amine, and MHI Japan developed called KS mixed amine. And then in China, by the petrochemical group developed called MA mixed amine. The heat regeneration decreased to 2.8 or to about 3 gigajoule per ton CO2, and it's also is high capacity and no energy and no degradation. And then we call this a new generation. We can call the third generation. That typical like the new mixed amines, phase change solvents, ion liquid based solvents, and the water-lone amines, and the nano field amines, and also catalyst aided amines. And this typical regeneration energy decreased to 2 gigafactory or 2.5 gigajoule per ton CO2. And but now it's most researched in the laboratory and also some pilot scale. So next step is demonstration projects operation. So for those solvents, our target is how to select good solvents. So we hope the solvents have high rate of reaction and mass transfer, high cycle capacity, and this can decrease the solvents flow rate and high to tau, and also will need the low heat of absorption and the low vapor pressure can decrease the solvents energy requirement and solvent loss. And also we hope to low byproduct formation and decomposition rate, so you can hope the solution is safety and low corrosivity. So also can benefit for the material selection and a high rate of biodegradation or low toxic, and it's good for environmental impact. So there are a lot of requirements for good solvents. How to compromise different requirement is one key. So so we say the first way actually is mixed amine. You know, now most of the operation projects is mixed amine. Mixed amine is just combine different amine with mutual promotion for high reactivity and low regeneration energy consumption. So two directions for mixed amine research. First is based on high CO2 reactivity, reduce the energy consumption. Typical one like you use MEA is high reactivity. And at the MEA, like at the MDA is a low energy consumption. So mixed MEA MDA is one mixed amine solvents. And second direction we use based on the low energy consumption, increase the CO2 reactivity. So this is typical like we use MDA, is low energy consumption, and then add some quick reaction like patching, PZ. Packaging is a very quick reaction. So in this become another new mixed amine. So like MDA and packaging is already widely used in the Europe country. It's a new solvents. So there are a lot of research about the new mixed amine solvents and a lot of is good result. So those results also combine the absorption performance and regeneration performance, and then become select the best one. So they are basically research on the absorption performance based on the regeneration performance, and then after the evaluation and get a good solvents. So and the second one, there are a lot of research we call solid generation. Here, typical one is a phase change solvents. So the phase change solvents is different with the common amine. Is after absorber, the solvents were divided in two phases, and for example here the down phase will absorb get the on the CO2 to the down phase. And then the down phase, because of the hydrogen bond and the cell effects, and then we just regenerate the down phase, and then because it's enough CO2 capacity and it's easy to regenerate, so this can reduce the regeneration energy greatly. So and then the upper phase just come back to the absorber. So there are the typical phase change solvents. One is we call the mixed amine phase change solvents. This amine means the solvents is on the composition is amine, and typical one like DEA and AEA, and DEA is AEA can after absorber can become a phase change, and but because phase change is energy, the lost energy can decrease to 2.2 gigajoule per ton CO2. But we found that one problem is down phase, the viscosity is very high compared to MEA. It's almost more than 50 times of the MEA. So it's one problem. So it's not a lot of research on how to decrease the viscosity to add some other new composition to decrease the viscosity. Because high viscosity will cause the flow pressure, and also the cause the heat exchange transfer decrease. And then another typical phase change solvent we call based on the physical and the chemical solvents. And the typical one, for example, is the chemical solvents MP and MEA, and physical solvents we call like one ether, called the DEG-DME is one ether, and also sulfate. And this here for this solvents, the MPME is a chemical solvents, and DEG-DME is physical solvents, and this also can become a phase change solvents. And this one the viscosity is acceptable. So it's almost some bigger than the MEA, but still it's not very large. Here, for example, here only 5 times of the common MEA, but the energy consumption can decrease to 2.5 gigajoule per ton CO2. So now it's people a lot of research think it's a very good phase change solvents. And now there are a lot of literature shows phase change solvents. So I just give some summary. For example, for the two part, one is amine, mixed amine phase change solvents, like for example, the primary amine is like usually TEA, AEA, and phase separation promoter is usually based on the DEA, and then the regeneration energy can 2.2, 2.4 like this. And then another one phase change called the physical and chemical phase change solvents. Then the primary amine, they are like MEA, BDA, DTA, and then the physical one like one kind of ether and sulfur, and then the regeneration energy can decrease to the 2.5, 2.6. So you can say the regeneration energy can decrease greatly. And then the energy consumption is one field, and another field how decrease the solvent degradation. And the degradation, typical include the oxidative degradation because of the oxygen in absorbed column to cause the degradation of the solvents, and also the SO2, SO3, and metal like different metal also causes the degradation quickly. And the second one is called thermal degradation. It's typically used in the dripper, you heating, and it causes solvent degradation. So oxidative degradation account about 70%, and thermal degradation account about 30%. And how to decrease the degradation? For first one, we found some inhibitor to control the oxidation degradation. And for thermal degradation, we usually control the temperature. So low temperature, low thermal degradation. So for the oxidation degradation inhibitor, there are a lot of mechanisms. For example, for example, is like a corrosion inhibitor, just absorbs the metal, and also the oxygen inhibitor absorbs the oxygen. Typical, so there are a lot of different inhibitor. So different amine have different inhibitor, and as a different result. So they usually just use some small quick test to make a selection of the degradation inhibitor. And this is we just shows some solvent development. Then second one we introduce the process optimization. Process optimization can decrease the energy consumption greatly. So for example, one typical one like we call the intercooling is absorber. Intercooling is during the absorber, the solution solvents amine and react with the CO2 to produce heat and cause the temperature increase. So intercooling is to cool down the solvents in the absorber. This can increase the leach loading at the absorber bottom. So this can, in this way, can decrease the energy. So low and no cooling temperature, and the energy consumption decrease largely. So it's also very effective to increase the remove efficiency of the CO2 for the absorption. And then second process we call, for example, for the leach spirit flow. So in the dripper, there are a lot of CO2 and steam when emitted from the top because of the heating process, regeneration process. And then for the leach spirit flow, we just inject part of the cold stream at the top of the dripper, and in this way can recover the heat from the regeneration CO2 steam stream. Then in this way can decrease energy consumption. And then we answer like MVR. MVR means for the regeneration process. They are the lens solvents, high temperature lens solvents is flashed in the container and then produce the gaseous stream and compressed and feed back to stripper. In this way can reduce the boiler steam demand. So for here, if we combine the process, intercooling is possible, leach speed flow and MVR. So totally, process can decrease the energy consumption about 20% for like MVA, can from 3.9 to 3.1 gigajoule. So it's a very effective. And second, we focus on how to decrease the capital cost. So decrease capital cost usually also can include there are some new reactor with no price material, and also there are some method heat transfer intensification process. As you know, for the absorber and the dissolver, it's a larger size and larger investment usually for the chemical absorption process. And because on the power use the stainless steel material. So for example, if we use the PP plastic packing to replace the stainless steel packing material, this can reduce the capital cost. But kind of concrete, if on the packing material use the PP plastic packing category is almost 50% cost. So it's a great advantage. But you know, PP packing, the problem is non-hydrophilic. So how to make the hydrophilic modification? We usually, for example, we add some material like MAH and also cause some microstructure on the surface. This can decrease. So use this technology, we can reduce the contact angle less than 10 and then so it's very good to keep the weighting of the material and good film forming, and also the material transfer is also increased very high. So also we research on the packing materials corrosion in the MEA or the new absorbent system, and show it's also very good for the PP packing material. Was almost the same with stainless steel packing, and now we already use this material in some projects. And then also we developed some called the enhancement of the heat exchange. You know, in on the chemical absorption process, there are a lot of heat exchange, but the temperature difference is very low. So we usually call the polite heat exchange. Polite heat exchange compared to the log traditional heat exchange, the heat exchange coefficient is very high. So almost double of the common tube heat exchange. And so then we design the different structure of the platter structure and also make a simulation and can, in this way, can greatly increase the heat exchange coefficient. So then decrease the investment or the cost of the heat exchange. In our lab, we have 200 cubic meters per hour flow gas CO2 capture plant. So in this pipeline, we use some plastic packing material and also to test, and also we use the new heat exchange to test, and also we test different new solvents. For example, we test with like MEA and mixed amine MA and the new mixed amine NE, and this already used in the Taizhou power plant. And as also we test the like phase change solvents in the already operated in the Zhejiang in our another projects. And for example, for this MA, we can the heat regulation heat can lost is 2.6. For NAE is 2.7, and unless we call the filtering solvents 2.4. So you can test here. After here, then we can go to project to operating. And then another a lot of research on the we call the pollutant emission. You know, there are a lot of amine emitted in the absorber to the aerosol. And then this can cause the solvent loss and a serious environmental problem. So now a lot of research for how to control the aerosol. And then our research found the flow gas nucleus concentration is the most important parameter to affect aerosol growth. If the flow gas, there are a lot of particles in flow gas, then they will grow up and become cause a bigger problem of the emission. So we should combine the flow gas cleaning and also the emission control together. So according to the literature, there are a lot of research already on the emission control. Typical one like dry bed, multi-stage water wash, and WSAP is and the mush type demister, etc. So on our lab also make research on the multi-stage water wash. So one method we use called water wash coupled dry bed, and then this one we add some mist emulated in the dry bed. In dry bed, the aerosol is effective become larger, and then use a water wash to capture the aerosol. So in this way, can decrease the amine emission almost more than 90% decreased. So, but this is already operated in some projects. And finally, I will introduce you some in the 150,000 tons per year CO2 capture demo project. It's a coal-fired flow gas. CO2 concentration is about 11, and oxygen 6%, and SO2 is 35 micron cubic meter hour, and particle 10 micron cubic meter hour, and NOx 50 micron cubic meter hour. And this is a typical process. This project we cooperate was like Professor Lu, and also the China Energy Group, and also a lot of the universities. And this project we use advanced solvents like mixed amine. When you mix amine and MA, and also we use the reactor like PP packing material, part of packing material, and also you high efficient prototype heat exchange. And also we use some intercooling, rich split flow, MVR, process the energy saving process. So this is a flow gas into the pretreatment, and then go to the absorber to absorb the CO2, and then we also have phase splitter system, and then we go to stripper to heating, and then the CO2 is recovered like this. And this project already operated in 2021, and it captures about 100,000 cubic meter per hour flow gas, and the regeneration energy consumption target is 2.4 gigajoule per ton CO2, and the capture efficiency is larger than 90%, and CO2 purity larger than 90%. And this is show you the efficiency, remove efficiency larger than 90%, and also we test the amine. We call it mixed amine MA, we found the generation energy is about 2.75 gigajoule per ton CO2 for this process, and also we found the solvent loss about 1.1 gigaton per ton CO2 during 30 days testing period, in which about 0.3 kilogram per ton CO2 emitted from flue gas, and then another is degradation loss. And also we use project use PP packing, and already after 2 years operating, it's still very good condition. And also we use some the fully weighted plate heat exchange, and this heat exchange can decrease the temperature difference to about 4 centigrade C. So it can for the heat and rich and run solution heat exchange. And also we use this process use intercooling process, leach split flow process, and the run vapor compression process. And we combine those energy saving process optimization, and the combine for intercooling with temperature 40 centigrade C and leach split flow 10%, and also MVR it's pressure difference 75 kPa, and then the legislation due date can decrease to 2.36 gigaton per CO2, so it's less than 2.4 gigajoule. So, and also we make the emission test for the facility, and we found the emission of the system of the amine emission about 40 to 60 micron per cubic meter, and under the ammonia about 4 to 6 micron per cubic meter. So it's still high. So next step will how to control the amine emission and ammonia emission. And we also found that if we increase the water flow, can decrease the amine and ammonia emission. And also we make an investment of the cost. We found that the total investment for this process is about 151 million yuan for total projects. And then we make the evaluation of the operating cost. During the cost, the total one about 216 renminbi per ton CO2 for about US dollar is 30. And so I will give a brief introduction. Conclusion is first, the CO2 chemical absorption is the main CO2 capture technology for CCUS. Development of new solvents, new loss, new cost equipment, and energy saving process can decrease the operating cost greatly. Further research is needed for amine emission control and solvent management. And finally, industrial utilization will promote the technology development, and how to realize long-time stable operation is very important step in the future. So this thanks the support of the national key and R&D program from China, and National Science Foundation of China, and some international cooperation projects. And so thank you. So Professor Long, it's finished of my presentation.
Okay, thanks for Professor Fang's excellent reports. Very fruitful research results have been achieved. Any question?
Hi, Professor Fang. Thank you very much for the excellent talk. So you have done a lot of comprehensive work on the amine scrubbing for the CO2 capture. So I have a general question. So I was wondering, so since you have done a lot of work to decrease the energy consumption for this process, but is there bottleneck now. So what do you think is the main the mean direction to decrease the energy consumption in this process? Thank you.
Yeah, thank you. The Professor Zhou's question is a very, very good question. And also now the most of research focus on this area. So, so as I mentioned in my presentation, now there are usually two ways. One way is development of the new solvents. So a lot of research focus on the new solvents development. Typical one, like with the phase change solvents, answer less water solvents, and also ion liquid. And so I remember the first day, second day, there are research on the ion liquid solvents, and also there are some like catalyst aided solvents and etc. And this is typical is the solvents development. So I think the solvents development already there's a lot of research, and the next step how to realize the industrial application is very important, because new solvents there are a lot of solvents can decrease energy consumption, but may cause another problem like degradation, like emission. So for this needed to verify for the industrial utilization. So, but I think those solvents, those may can the lost now according to the literature is about 2 gigajoule per ton CO2. So it's the lost one. Yeah. So we're waiting. Already there are a lot of projects were realized in this year or next year, and this is the first direction. And the second direction is we say is we call the energy saving process. So in the project I introduced Professor Lu. Also here we do a lot of research on the energy saving process, and but this process in Zhejiang power plant, the project is only small one. So we just use the energy saving process in the short-term process energy saving. But also shows it's very obviously we can decrease the almost 20% energy decrease energy generation energy. So it's greater. So next step for larger one, for example, in the Wallen group, we see one developed 1.5 million ton per year CO2 capture projects, and also in the petrochemical group and the petro-China, also we see one developed 1 million ton CO2 project. This project may combine the total power plant system, and in this way, maybe can still decrease energy consumption, maybe more than 30%. Then you say the combine together. So it's maybe we can in the future we can decrease energy consumption for the regulation energy maybe less than 1.8 or like this. So it's a good direction also. So it's I think it's a typical tool way. Thank you.
Yeah, thank you. I think we are also waiting for the further development of this technology. Thank you very much.
Okay, any question?
And Zhejiang, can I ask a question?
Okay.
Professor Fang, thanks for the excellent talk. So my question is about the comparison between liquid-based absorption and solid-based adsorption. So I think you have many experience like to commercialize the liquid-based absorption technologies. So from your experience, what's the future of, like for solid-based adsorption? Because we understand there are less commercial plans for solid-based adsorption. So can you comment on that regarding the future developments for the solid side?
Okay, thank you for Professor Wu. And so now I mentioned that now most of project is aiming scalable and chemical absorption process because it's easy for larger scale and only this technology is so mature. And then there a lot of research focus on solid absorption process. And from the cereal, solid absorption don't need the steam, so it can decrease the energy consumption. So there solid absorption we can like the low temperature, like the solid amine and etc. And then middle temperature like some metal like sodium carbonate and high temperature like limestone, calcium carbonate, etc. And but I think so there are a lot of now the solid absorption plus is now focused on the solid material based on in the laboratory. But for industrial utilization, now looks some difficulty. So as you know, we also cooperate with Professor Low on later elect solid absorption process in Jingjie. It's 1,000 ton per year projects. But its Abdul law is still not work well. The problem is for solid absorption process. If for chemical absorption, then the heat exchange is some difficulty. So in our process we use two fluidized bed. One fluidized is absorption, absorbed CO2, and another fluidized bed is degenerated CO2. And then we found the solid circulation, actually attribution the very large. So for fluidizers, the one problem is attribution quantity is too large, and so we think that the solid processing process mainly maybe focus on fixed bed, maybe is better fixed bed. But the fixed bed is the problem is how to solve the heat exchange for chemical absorption process. So it's a one problem. So I think now most of the solid absorption process is use fixed bed, is use the physical absorption like cellular, carbon material, etc. So I think now the main problem is the solid absorption is for small scale. It's okay, high pressure, high concentrated, but for flue gas, then for fixed bed, so how become the larger is the process, the system, so it's some difficulty. So I think now people mainly focus on the material. So I hope the people maybe focus on the process as a reactor. Is also very important for the commercialization of solid absorption process. Oh, thank you.